Today we are going to discuss one more important chapter for physical chemistry, that is ionic equilibrium. First question based on JEE pattern is little textual. The question is the extent of ionization increases with the various options being provided to us. Now we know that if I take any weak acid or weak base, or I mean to say any weak electrolyte undergoing the dissociation in water, which is a pure liquid, you will be getting the conjugate acid base pair. Now we know when I have started this initially the dissolving process by taking C molar of acetic acid, and as it reaches the equilibrium, let's assume that the degree of dissociation is alpha, then the fraction of the acetic acid remaining is 1 minus alpha of C, and C alpha and C alpha moles of acetate and hydronium ion are obtained because they are reacting in 1:1 mole ratio. Here we are not concerned about the pure liquid, that is H2O, because its active mass is being taken as 1. Now when I am writing the acid dissociation constant, I will write the concentration products of the products and concentration of the reactants. Hence I will be getting this expression where I say that here the alpha value is, I am assuming it to be negligible compared to 1. Here the point is, you can do this only when alpha, which you calculate by means of the simplification, is less than or equal to 0.1 only. So this is a hint that I am providing you, that you can do this negligence, or this alpha can be negligible compared to 1 only if the equation is satisfied with the values of this alpha being calculated as less than or equal to 0.1. Now when I neglect it, I will be getting Ka is equal to C alpha square, or alpha is equal to square root of Ka by C. This is the expression which I gave you. So as per this expression, you can see that the value of alpha is supposed to increase with increase of Ka, as we know that the dissociation reactions are endothermic by nature. So the Ka value can be increased by increase of temperature as per Van 't Hoff equation. So temperature increases the Ka, hence temperature also increases the dissociation. So alpha is affected by the increase of Ka or increase of temperature, or even by the decrease of concentration. I mean to say decrease of concentration increases value of alpha as per this expression. Decrease of concentration is nothing but increase of dilution. What I mean to say that when I increase the dilution, I mean to say the water content in the given solution, I can expect here the alpha value to rise. So therefore correct answer for this question is answer B, where you say that when you add excess of water, I mean keep diluting the solution, you will be getting more value of alpha for any electrolyte dissociating in a given solvent. Now we have a weak acid and the hydrogen ion concentration is asked if the Ka value is given. Just now, as we have discussed in the previous question, we can see here the weak acid dissociating partly into acetate and H plus ion. So I have taken the concentration to be C at equilibrium. Directly I am writing the concentration of these two, C alpha and C alpha, and we have just seen that the value of alpha is turning out to be square root of Ka upon C. Therefore concentration of H plus here at equilibrium, you can see, is C alpha. When I am substituting here the value of alpha to be square root of Ka upon C, the concentration of H plus is turning out to be square root of Ka into C. Sometimes when the pH values are asked, when we substitute the negative logarithm of concentration of H plus, we get this as minus 1 by 2 log Ka into C. So now since in this question the concentration of the hydronium ion or the hydrogen ion is asked, you can say that the answer for this question is option D. So at 90 degrees Celsius, pure water has concentration of H3O plus 10 to the power minus 6 mole per liter. Its value of Kw at 90 degrees Celsius is asked. So here we know that water undergoes self dissociation to give the H plus or H3O plus ions along with the OH minus. So therefore, when I am writing the equilibrium constant, the concerned equilibrium constant for this, I am going to get this as the concentration of the products divided by the active mass of the pure liquid is always being taken as 1. So here we call this as the self dissociation constant or autoprotolysis constant of water. Now here it is given that concentration of H3O plus is equal to 10 to the power minus 6 molar, and we also know the fact that water being neutral, the condition is that the concentration of H plus and OH minus should be equal. Then in that case, when you substitute here the values, you are going to get 10 to the power minus 6 into 10 to the power minus 6 molar square, that is 10 to the power minus 12 is the value of the Kw. So therefore, the right answer for this question is option C. The pH of a solution is 5. To this solution, sufficient acid is added to decrease its pH value to 2. The increase in hydrogen ion concentration is asked. So we have a solution whose pH, which is calculated as negative logarithm of concentration of H plus, is given as 5. And we know that when you are adding the acid, that is when you are increasing the concentration of H plus ions, the pH value decreases. So here you can see the initial pH was 5, the final pH is given to us as 2. So therefore, change in pH is by 3 units, that is pH 1 minus pH 2 is given as 3 units. By writing it equal to the concentration of H plus ion, we can see that the concentration of H plus ion is turning out to be 10 to the power minus 3 molar. This is the concerned change which is taking place when we are adding the corresponding acid, or we can say that the value of pH will decrease only when the acid is added, and the difference is considered to be the amount of times the concentration of H plus being added. Now you can see that the difference, since is 3 folds, we can say that the concentration of H plus is increased by 1000 folds. You can see here the variation is 1 by 1000, or the concentration of H plus which is added to be 1000 times the initial value. Then we can incur such a change in the pH value. So the right answer for this question is option B. Now we have a solution which contains 10 ml of 0.1 normal NaOH and 10 ml of 0.05 normal H2SO4. Then the pH of this resulting solution had been asked. Now we know that when I am treating H2SO4, when I am mixing the aqueous solutions of acid and base, they are going to participate in the neutralization reaction to give you the salt and water. So now when I look at the gram equivalents or milli equivalents of this H2SO4, which I will get by multiplying the normality with the volume of solution in liter. Now we know that the normality of H2SO4 being mentioned as 0.05. When I multiply this with the volume of H2SO4 solution, which is being taken as 10, these are the gram equivalents. Normality equal to number of equivalents divided by volume in liters. So therefore, when I am willing to find out the gram milli equivalents, I should substitute the volume in milliliters. So therefore, I am multiplying this normality with the volume so that I can get the milli equivalent. The normality is given as 0.05 and the volume is 10 ml. Now we have NaOH whose concentration is given as 0.1, normality once again into 10. Now these two are about to react. Now we can see clearly that this value is turning out to be 0.05, whereas this is 1. Now when these two react, obvious that this is going to be the limiting reagent, because its amount reacting to be less. So therefore, equivalence of NaOH reacted is also same as that of H2SO4 as per law of chemical equivalence. They are nothing but 0.05. So therefore, equivalence of NaOH remaining are initial and reacted, that is nothing but the difference between the two is 0.05. So here, after finding out the resultant NaOH, the concentration of NaOH that we would obtain is gram equivalents or milli equivalents of the NaOH divided by total volume added is 10 plus 10, that is 20. Now when I have to find out the pOH value, negative log of concentration of OH minus, which is nothing but negative log of concentration of 0.05 upon 20. Now when I am doing this, I will be getting the pH value greater than 7, because in my solution I have this as the excess reagent. That means the solution has the excess base ions present, so therefore the pH will tend to be greater than 7. So the right answer for this question is option C, that is the pH value greater than 7. Now we have a question in which the solution whose aqueous solution is basic is being asked and concentration is given. Now we have various options A, B, C, D. And if you take option A, we have the compound ammonium acetate, that is CH3COO NH4 is going to dissociate into CH3COO minus and NH4 plus. To be more precise, this is not a reversible reaction because it is completely soluble. So when this is a strong base, as its conjugate acid is being weak, so therefore being a strong base, it will abstract proton from the solvent to give you CH3COOH plus OH minus. Now this is a conjugate acid of ammonium hydroxide, which happen to be a weak base, so therefore this will also react with water to undergo hydrolysis to give you NH4OH and H plus. Now we know the fact that these two are going to react further to give you H2O. I mean to say, this solution has acetic acid, ammonium hydroxide and water. So therefore the solution pH is going to remain at 7. Now the second thing is ammonium chloride. So when I have ammonium chloride, it is also going to dissociate into NH4 plus and Cl minus. Now when once again we know the fact that ammonium hydroxide is a weak base and hence this will be a strong acid. As we know, this is a strong acid, is going to react with water. It's going to abstract the proton to give you NH4OH plus H plus. But we know the fact also that this is the conjugate base of HCl, which happen to be the weak base because HCl is a strong acid. So therefore this is nowhere in a position to abstract proton from water. So the resulting ions are H plus, so therefore pH of this solution will be less than 7 as far as the option B is concerned. I mean to say the solution will be acidic. Now you have the third option, it is something like this only, except the fact that here instead of the chloride ions, the sulfate ions are present, which are going to resemble in properties with the chloride ion. Now we have the last option, that is option D, sodium acetate. It's going to dissociate into CH3COO minus when sufficient water is added. And we know that this Na plus is the conjugate acid of sodium hydroxide, which is a strong base, hence this is a weak acid, not going to react with water. But this is the conjugate base of a weak acid, that is acetic acid, hence it's a strong base going to react with water. So when I treat it with water, the resultant ion produced are OH minus, hence the pH will be greater than 7. So therefore the solution whose pH is greater than 7 or whose nature is basic will be that of the acetate. So the right answer for this question is option D. About buffer solution, which of the following statement is correct? We know that the buffers are being classified into 3. One you call as acid buffer or acidic buffer, which is the combination of the weak acid and its only salt with any strong base. I mean to say, you have got say CH3COOH and its only salt with a strong base, and its aqueous solution is going to act as a acidic buffer. You can take H2CO3 plus HCO3 minus or NaHCO3 is nothing but the blood buffer. We have got H3BO3 and Na2B4O7 acting as a borax buffer as well. So this is an acidic buffer. Then we also have the basic buffer. So we know that the pH value is going to be less than 7 here. If the buffer is basic, the pH is going to be greater than 7. So we have a weak base and its salt with a strong acid, the combination is going to pretend as a basic buffer. The third one is neutral buffer, is nothing but the salt of the weak acid and weak base. Like you have acetic acid is a weak acid and ammonium hydroxide is a weak base. The mixture of these two is going to yield us the salt, which is going to act as a buffer, which is not going to change its pH when little amount of acid or base is added. Now when I am adding the H plus ions or OH minus ions to the solution, since they are being the strong bases and strong acid respectively, because they are the conjugate acids of the weaker one, they are going to abstract the protons or the OH minus that we have added over. So therefore there won't be any change. So therefore we say that buffer is going to show little change or almost no change when small amount of, remember my dear friends, that we are going to add only small amount of acid or base. You can't expect that there won't be any change in pH when you add huge amounts of acid or bases. So the right answer for this question is option C. An acidic buffer solution can be prepared by mixing solution of a weak acid, the aqueous solution of a weak acid and its only salt with a strong base. So here when you have taken this combination, this is going to dissociate feebly in water to give you the acetate and H plus ion, and sodium acetate being a strong electrolyte is going to dissociate completely to give you these two. Now when I am adding small amount of H plus, will shift this equilibrium by the consumption of acetate ion in the backward. When you are adding the OH minus ions, the OH minus are going to combine with this to produce H2O and the equilibrium will be shifted in the forward direction. That's called buffer action. So when you are adding H plus ions, it's being nullified, or when you are adding the OH minus ions, it's also being nullified. So therefore it's called as a buffer. So the right answer for this question is, as we discussed, acidic buffer is a salt of sodium acetate and acetic acid, that is weak acid, and salt with a strong base. A certain buffer solution contains equal concentration of X minus and HX. The Kb value of X minus is given to us as 10 to the power minus 10. Then the pH of the buffer is asked. Now we know that the HX and X minus combination, that is the weak acid, and it's solved with a conjugate base, is going to act as an acidic buffer. So therefore when I am writing the concerned equation, as we know my dear friends, that we are going to calculate the pH of a buffer by using this expression, which is called as Henderson-Hasselbalch equation. Now to find the pH of the solution, we need the value of Ka, and we know the fact that suppose I have got a weak acid, say I have taken HX, is a weak acid dissociating partially, right? Now when I am writing its reaction, I am going to say that when I am considering the autoprotolysis of water, you know that this is going to be Kw. So when these two are reacting, you know HX plus OH minus is in equilibrium with X minus plus water. This is what we call as 1 by Kb, because the reverse reaction is nothing but the basic nature of X minus. So therefore we say, as per equilibrium rules, Ka into 1 by Kw is equal to 1 by Kb, or Ka into Kb, I am going to say Ka of Hx into Kb of X minus is always equal to Kw. Now from this relationship we have been given the Kb of X minus, so therefore Ka into 10 to the power minus 10 is equal to 10 to the power minus 14. Kw value I am writing at 25 degrees Celsius. So we know that the Ka is turning out to be 10 to the power minus 4. So there when I substitute here with the equal concentration of the salt and the weak acid, you are going to get this one as 0. So pH is turning out to be 4. So therefore correct answer for this question is option A, that is pH equal to 4. A mixture of weak acid and its salt with a strong base is a buffer solution. Which other pair of substances from the following may have similar properties? So acidic buffer is a mixture of the aqueous solutions of a weak acid and its salt with a strong base. Let's pick the options now. We have HCl and NaCl. We know that HCl is ruled out because it's a strong acid. We have NaOH and NaNO3, not at all possible because NaOH is a strong base. Now we have KOH and KCl, once again not possible. The last option, option D, seems to be a little reasonable because we have got the combination of the weak base, that is NH4OH, and it's only salt with a strong acid, that is HCl, giving rise to the salt. So therefore correct answer for this question is option D. We have 1 liter of a buffer solution containing 0.01 molar ammonium chloride and 0.1 molar ammonium hydroxide having pKb equal to 5 has a pH of. So we have got a basic buffer question. To find the pOH or pH, we will be using this expression, the concentration of salt upon concentration of a weak base. In this question, the pKb value directly is given as 5 plus log of concentration of salt, which is being mentioned as 0.01 upon 0.1. Let us say when I simplify this, I am going to get this as 5 plus log 0.1, that is 5 minus 1, 4. So when pH is needed, we subtract the pOH from this. So the right answer for this question is option B, that is pH equal to 10. Now the question is based on the solubility and solubility product. A precipitate is formed when the options given. So we have, say, a sparingly soluble salt MxNY represented as S. S mean to say that it is solid, is insoluble in water. If it is soluble, we would have mentioned this as AQ, that is aqueous. Now when it comes to its dissociation, you have got X moles of M plus Y and Y moles of N minus X are being produced. Now if I assume that the solubility of this salt as S mole per liter, that means S moles of this particular salt are dissolved per liter of the solution. Since it is not going completely into the solution, we have to use our stoichiometry to write here, for every 1 mole we are getting X moles, for S we will be getting Xs and Ys. Now we know that when I write the equilibrium constant Ksp, I will be writing the concentration of M plus Y whole power its stoichiometric coefficient and concentration of N minus X whole power its stoichiometric coefficient. It's turning out to be X power X into Y power Y into S power X plus Y. Now whatever I have written this side is called as ionic product, is something like Q, and this is nothing but your solubility product. So when I am comparing the solution, when you say that Q is equal to K or the ionic product is equal to the solubility product, we call this as, with this combination, what we call as the saturation point or saturated solution. That means the equilibrium is achieved as far as dissolution is concerned. Now the second point is Q less than K, or ionic product is less than that of solubility product. That means it is unsaturated or the reaction is still moving in the forward direction. And third point is when you have exceeded the prescribed value, that means ionic product is greater than solubility product, you call this as super saturated solution. That means we are moving in the backward reaction. So when I am carrying out the backward reaction, that means I am precipitating the given salt once again. So the right answer for this question is option D, where the precipitation is done when the ionic product exceeds the solubility product, that is Q value greater than K. The solubility product of an insoluble salt A2B is given as 4 into 10 to the power minus 9 mole per liter whole cube. Then its solubility is being asked. Now we have the insoluble salt dissociating as just I specified, 2 moles of A plus and 1 mole of B minus 2. So if I assume that the solubility of the salt as S mole per liter, you are going to get 2S mole of A plus, because for every 1 mole you are getting 2 moles, for every S mole dissolved you will be getting 2S and 1 S mole. So therefore Ksp of this equilibrium is A plus square into B minus 2, that is 2S whole square into S is being taken as Ksp, that is 4 into 10 to the power minus 9 is equal to 4S cube. Now when I simplify this, S because 4 gets cancelled and it is turning to be 10 to the power minus, I mean you are going to write it as 10 to the power minus 3. When it comes here this side, it is going to convert into 10 to the power minus 3 molar. So the correct answer for this question is option A, that is 1 into 10 to the power minus 3 molar. Solubility product of barium sulfate is 1.5 into 10 to the power minus 9 at 18 degrees. Its solubility in water is asked. So we know that barium sulfate we are going to dissociate as barium plus 2 and sulfate ion. So when I am writing KSP, or when I assume that the solubility of this salt is S, you are going to get S square as KSP. Now we know that the S square value is given as 1.5 into 10 to the power minus 9. The KSP value is given to us. So therefore the solubility, when I simplify, is going to turn up as 3.9 into 10 to the power minus 5 mole per liter. So the correct answer for this question is option D. We have pure water and it is asked what happens to its pH and pOH when the temperature is increased. As we know that water is going to dissociate into H plus and OH minus ions. So the dissociation is endothermic by nature. So when I am increasing the temperature, the dissociation of H2O is increased. Therefore, the concentration of H plus and concentration of OH minus is supposed to increase proportionately. So when concentration of H plus is increasing, pH is equal to negative logarithm of H plus ions, or pOH is equal to negative logarithm of OH minus values are going to decrease, because you can see it is minus log of, hence I am increasing these two values will decrease the pH or pOH. So the right answer for this question is option D. Now we have 10 to the power minus 10 molar NaOH solution at pH is being asked. Now when we have any acid or base, concentration if less than or equal to 10 to the power minus 6 molar, that means very low, then consider the H plus or OH minus concentration coming from H2O also. What I mean to say, in this current case you have NaOH dissociating into Na plus and OH minus. The concentration of this was being taken as 10 to the power minus 10 initially, then completely dissociation gives you the equal amounts of both Na plus and OH minus. Now we know that this, when I directly substitute as pOH is equal to negative log of concentration of OH minus, is turning out to be 10. So when I do pH, which is indeed an incorrect option. The reason that the pH of a base always has to be greater than 7. Here this mistake has incurred because we haven't considered the dissociation of H2O. Now when the concentration of acid or base is very much low, we have to consider the dissociation of H2O also, from which we will assume that X mole per liter of H plus or OH minus are being emitted out after the common ion. After the common ion effect, we say that the concentration of OH minus which is obtained from what you call this NaOH or H2O will be very, very less. Now when I write the total concentration, I am using the common ion effect here. So when I am writing the concerned equilibrium constant Kw equal to concentration of H plus into concentration of OH minus, and so when I simplify this to obtain the value of X, the positive value is only being considered. When you do X is equal to minus B plus or minus square root of B square minus 4AC by 2A, I will be getting the value of X. So there are two values that are supposed to be obtained, one is positive, the other is negative. I will be taking the positive value of this X and I will be substituting in the pOH equation, because we can't neglect the value of X because the concentration of the base itself is very, very low. When I am substituting here and when I am subtracting this pH, the pH is supposed to be greater than 7 as the solution is basic. So it will be greater than 7 but close to 7. So the right answer for this question is option B. So if it is asked to find how much it will be, you have to just substitute the value of x over here. It will be 7 point something.